All right, we are back. All right, so let me go get Moodle. And let's see, last time we managed to, yeah, we went through the chapter 11 problem sets 1 and 2, and those are completely done. So we're completely done with chapter 11, our discussion about probability theory. Now, when our a little Zoom meeting fell apart here, I was attempting to show you 2 videos, and so I had to email them to you, and so I hope you're able to watch them. One of them was the banana, the last banana. And the other one was that comedian who actually was making his entire routine based on statistics. It's kind of hard to imagine, but you can see this guy is good. He makes his living doing, or at least I guess, I don't know if he makes his living, but he specializes in jokes about very serious subjects. And it's surprising how he's able to do this, but you can find him on the internet. In fact, one of the things he does well too is he has a series of videos about how to do better PowerPoint presentations, and he shows you what people do wrong, and it's pretty hilarious. So he's a very interesting comedian, to say the least. So now today, the next 2 that we should look at when we're ready are this one you can see here, mean, median, and mode, and then this one, which is called correlation doesn't equal causation. So that'll have to take a while before we get to that point. So anyway, so today what we're going to do is get back to chapter 12, which is our introduction to statistics. And that, by the way, is the last chapter of the course. When we're done with chapter 12, the only things we have to do left would be then to do the chapter 12 problem set, or there might be 2, I've forgotten. And then we'll do the sample final, and then we'll have our actual exam. Now, I think the official finals week, let's just double check it. Let's make sure. Now, of course, normally in a normal semester, when everything is done in person, we would be in the physical classroom. And according to the schedule, we'd come in during the week of the 13th and sit down and have our exam in the classroom. But under the circumstances, that sort of all goes out the window. So what we can do here is, as soon as we're done with the sample final, I can just basically post the final exam, and then you can send it in the normal way. But if we finish early, which is a possibility here, then we probably would just not have to bother holding, let's say, our last session. Instead, it would be due during the normal week, but you might get extra time to work on it. Okay, so in other words, if we finish early, then I will just post the final as soon as we're done. There's no point in waiting until the week of the 13th. But the exam, no matter when you have it, it would certainly be due during this week of the 13th. Okay, so you have plenty of time to finish it, is what I'm saying. But I suspect that we move along pretty quickly this semester, that there's a very real chance that we might be finished before the semester officially ends. And if that's the case, well, we can either do some extra reviewing or, simply not have the last class whenever that happens to be. So we'll see how that goes. But in the meantime, we're going to get back into statistics. And we've really just barely started it. So we may as well go back and revisit it. Let's see. It's in here somewhere, I think. No, actually, I guess, oh boy, it looks like I never posted it. All right, well, let me take care of that right now. Yeah, it looks like I forgot. Yeah, the videos are up here. All right, and if time permitting, we'll take a look at least the mean, median, mode video. That we might have time for that today. If not, it can certainly wait till next week. Which next week, of course, don't forget, there's not going to be a class on Thursday because, of course, that's Thanksgiving. But we do have a class scheduled for Monday, as usual, and we will, of course, spend that whole session on chapter 12. All right, so it looks like I did not post chapter 12, so I'm going to take care of that right now. Okay, so these announcements are all pretty much caught up. So let's see. All right, let me go into my archives and find chapter 12. Okay, here it is. All right, let me just post it. And while we're at it, oh, it looks like there might only be the one problem set, but I can certainly write more practice problems for you if we need them. We'll start with this one. Let me just post this right now. And, time permitting, maybe I'll write some more questions so that we can get more practice, which of course is always good. All right, but for now, that should be enough. And then later on, of course, I'll post the sample final, and then we'll be looking at that after Thanksgiving, of course. All right, so what's going on here with statistics? Now, statistics, you hear this all the time. You hear about it all the time. It's a very important branch of mathematics, and it is intended to be useful. Now, not that other forms of math are not meant to be useful, but this one is particularly geared towards trying to explain what we observe in the real world. So a lot of these techniques that we are going to learn were developed for the express purpose of explaining what's happening. The statisticians who invented these techniques were trying to explain something specific that they observed in the real world. And the techniques that they came up with proved to be very useful for many other applications. And so that's why we keep using them. So it's closely related to probability theory because we're still at some point trying to essentially estimate or guess what might happen in the future based on information we have today. But the techniques we'll be using here have been used for many centuries to help understand what happens in the real world. And it's particularly useful in disciplines like finance and economics, but also in some of the social sciences like psychology, and in some of the sciences like the harder sciences like biology, let's say, because statistics is useful for just drawing observable data and drawing conclusions from it. Or in the case of biology, carrying out experiments and drawing conclusions from the results of those experiments, or psychology as well. In psychology, certain types of experiments can be performed, and then the data that they generate is analyzed with statistical techniques to understand exactly what they found. Now, in some fields like economics and finance, we can't really conduct experiments. So instead, what we try to do is gather up all the data that we can and try to understand what it's telling us. So this is something that you'll see in just about every discipline. And even if you don't use it in your own major, you'll read about it. If you're trying to keep up with, let's say, what's going on in the financial markets, let's say down the road, you're very successful and you have plenty of money to invest and you're watching the stock market, you'll discover pretty quickly that a lot of the information that's being presented to you is some kind of a statistic. It was gathered up from real world data. So it's very helpful to understand what these measures are actually telling us, not just for academic purposes, but for helping you understand your own personal finances. So it's a very important area of study. Now, most schools, including Purchase, do have an entire semester of statistics that you can take in the math department if you find this material particularly interesting, or if you might need it for some reason. For example, I think they have a major at Purchase, arts management, I believe it's called, and anybody who's involved with management in any capacity would be very well helped by having a better understanding of statistics, because a lot of the information you'll encounter is actually based on statistics. So anyway, with all that being said, it's a very important area, a little different from other branches of math because the focus is on trying to understand what's happening in the real world. So ultimately now, what are we trying to do with statistics? We're trying to draw conclusions about a population of data from a sample that was chosen from that population. So we have to make a distinction in statistics between samples and populations. Most of the time, we'll be dealing with sample data because population data tends to be very, let's just say there tends to be a lot of information in a population, maybe too much for us to realistically analyze. And so what we often do is we resort to samples, which are chosen from that population, and we study the properties of those samples. Like here's a good example. The government, let's say the government wants to know if the average life expectancy in the United States has increased in the last 10 years. It's important for them to know that because, you know, obviously the longer people live, the more money the Social Security system will pay out. And we don't want it to run out of money, do we? No. So luckily, you know, this should come as a shock to no one if all of a sudden everybody's living to, you know, much longer than in the past. We have this information in front of us and we can see that people are healthier than ever and they're living longer. And so therefore, you know, they have to make provisions for increasing spending on Social Security in the future. So they can find out if the average age is going up by actually analyzing every single person who lives in the country. But that could take an incredibly long time. So what they might do instead is say, listen, we don't need to observe all 330 million people. Why don't we try this? Let's choose a sample, meaning we randomly pick people from the population and use their ages to represent the average age of the people who live in the country. Now, as long as we choose the sample carefully, that should give us some good results. Okay, so the important detail with sampling is that while it can save us a lot of time, if the sample itself is not chosen well, it could give us deceiving results. So like here, for example, what if my sample consists of only college students? Well, that would be a very poor choice because obviously college students as a whole are younger than the overall population. On the other hand, what if I pick only people who are retired for my sample? That would also be a very bad idea because obviously by definition, they're older than the rest of the population. So I need to really and truly pick a truly random sample where the sample itself very closely reflects the overall population. For example, they could just say they could take a list of Social Security numbers and randomly pick 10,000 of them and use that as their sample and come up with an average age, which they hope is very close to the age of the entire country. If they've done this correctly, they've saved themselves a lot of time and money, and they'll get a very good estimate of the average age of the US population. But again, like I said, if they haven't chosen the names well, then they'll end up with very inaccurate results. So sampling is a very important part of this. Now, we're going to assume in this chapter that the sampling has been done correctly. So the sample data that we have actually does reflect the population. If not, that's an issue for a separate class. That's a much more advanced topic that we don't want to deal with here. We're just going to note here that a sample is taken from the overall population, and ideally, it should very closely reflect the actual population. If so, the results that we obtain should be very accurate. All right, so more formally, a population is a collection of measurements or outcomes of interest. A sample is a subset of a population. Remember, we defined this in the previous chapter. A subset is contained within a larger set. Now, I do want to point out here that the word population normally in everyday usage indicates a group of people. Here we're using it in a somewhat different way. We're really studying not so much people, but characteristics of those people, like their ages or their incomes or their heights or their weights or how much they spend on groceries every week or you name it. People, there's a lot of useful information about people that could be studied by, let's say, the government or by marketing research firms. Like you can imagine that most large corporations need to understand what their customers want. And so they do a lot of research to find out, like how old are they, where do they live, how much income do they have, and all this and that. That helps them plan their marketing campaigns, and it also helps them decide what new products they might introduce. So let's say that you are Starbucks, and you say to yourself, it's time for a new drink. We haven't had a new one in a while. What do you suppose people want to drink? So they start doing surveys, and they'll ask people, well, what do you think? What if we offered you these flavors? Would you like them, or would you like to buy them? And so they have to do research and find out, what the public wants before they decide what new products to develop. And other companies might say, well, the products that we sell depend on there being a large school-age population. We want to make sure that that's going to continue into the future before we develop any new products. So populations are much, let's say in statistics, the word population is a much broader concept than it is in everyday usage, where it usually refers to people. Just keep in mind here, the word population usually means measurements of some kind. In other words, numbers. Although it doesn't have to be numbers, by the way. It could be, like, for example, suppose that Apple decides one day, you know what, it's costing us a lot of money to have different colors for our iPhones. Why don't we just pick one color and stick with it? Well, how would they decide what color to pick? They'd have to do a lot of surveys and find out what people like, what color they prefer before they make a decision. Now, in fact, it's actually going the opposite direction. I was just looking at Apple's website last night, and their new laptops, all of a sudden, they come in like 8 or 10 different colors, which I've never seen that before. They used to always be silver. And now all of a sudden, they're like, well, what do you want? You want orange, you want yellow, you want red, you want blue, and all this and that. Well, why would they do something like that? What must have they discovered during their marketing research? They must have found out that people told them that they would prefer to have a choice of colors for their desktops. And so Apple said, no problem, here they are. Of course, we're charging you more money, but here we are. So this comes from this information that they gathered from surveys. And in those surveys, they are looking at a sample because they can't possibly survey every single person in the country. So they're using the survey data as a type of sample, which is drawn from the overall population. All right, now, let's see. Let's jump ahead and, okay. Oh, by the way, I put in here a very interesting side note about marketing research that turned out to be a disaster. And this is something that happened about 40 years ago. And even now, you might meet people who still remember this disastrous decision by Coca-Cola. In the early 1980s, Coca-Cola was concerned that they were losing market share to PepsiCo. Of course, PepsiCo is their primary competitor. Both of these drinks have been around since the 1890s, and they've always been the two big names in the soft drink market. And, they've expanded and become gigantic corporations. And along the way, they both acquired a lot of other brands that you're very familiar with. For example, Mountain Dew, if you've ever had it, belongs to Coca-Cola. I think no, wait, that might be Pepsi. Let me see. If you looked on the internet, let's do this for a second. Now I'm thinking about it, I'm not sure. It is Pepsi. Okay, I wasn't sure. So in other words, if you go to the store and look at all the different soft drinks that are available, the majority of them are actually owned by either Coke or Pepsi. So let's, just for the fun of it, let's see if we can find a table. All right, so this is Pepsi. Now, okay, these aren't all sodas, but you see they own Quaker Oats, Tropicana, I don't know this one. But this is how they stay on top. This is how they expand their market. they don't develop, in a lot of cases, their own new products. They buy up existing products and add them to their empire. Oh, look at that. I did not know. I figured Starbucks owned its own vegetable. Look at that. Those belong to PepsiCo. Huh. Gatorade. Look at that. Oh my God. Now, interestingly enough, most of Pepsi's profits actually come from their snacks division. So these Doritos and Cheetos, these represent a huge percentage of their profits. You wouldn't think so. Oh my God, they own Life. Oh, Lipton, they own, man. Sierra Mist, Mountain Dew is one of theirs. Now, how about Coke? Let's see what Coke owns. All right, now they have, as you can see, there's a huge list there. Of course, they have Sprite. Okay, that's what it was. Sprite is Coke, Mountain Dew is Pepsi. Okay, I forgot. Fanta is Coke. That's orange soda. Man, look at all these things they own. Minute Maid. Okay, so you see, like one company has Tropicana and the other has Minute Maid. You see, they both feel that they must compete in every one of these markets. If one buys an orange juice, the other has to buy an orange juice. And because PepsiCo made that deal with Starbucks, well, naturally enough, Coke has to have its own. Georgia Coffee, I don't know that one, but it's a coffee, isn't it? Costa Coffee, Fuzz Tea. Jeez, look at that. Schweppes, oh my God. I didn't know about that one. Anyway, Fresca, yeah, Fresca is it's like a lemon drink. Now, there still is Barks Root Beer. What do you know? There's still one somewhat independent. Dr. Pepper and Snapple got together. That actually is a separate company. They don't belong to either one of them. Keurig, and they own Keurig too, the coffee machine makers. Keurig, Dr. Pepper, and Snapple is a separate company. But for the most part, Coke and Pepsi are the gigantic players in this market. So whatever one does, the other feels like they have to do it too. And so they're constantly keeping an eye on each other and saying, listen, what are they doing over there? Oh, and they try to find out, and they try to do the same thing themselves. Now, in the 80s, Coca-Cola was concerned that they're losing market share to PepsiCo. And then, it happens. They go through these streaks where one company starts to do better, and then the other one buys something up. Now, Coke and Pepsi, like I said, have been around a long time. Coca-Cola was originally, believe it or not, intended not to be a soft drink, but it was meant to be a medicine. It was meant to be something you would take when your stomach was upset. And it was, after a while, it became clear that people liked the taste so much that they started promoting it as a soft drink. So it wasn't, at the time that Coke came along, people in general didn't drink beverages that were quite as sweet as maybe now. So Coke was always worried that Coke wasn't really sweet enough to compete with Pepsi. So they developed in their marketing division this new flavor called New Coke, which is a little bit sweeter than regular Coke. And they figured, well, you know what, this will help us compete with PepsiCo. So they did a lot of test marketing. They asked people, like in blind taste tests, which do you like better? And they didn't tell them which was which, of course. And they found that the research said most of the people preferred the New Coke to the traditional Coke. Now, here's where things went off the rails. Those knuckleheads at no point told these people that they were thinking about replacing the traditional Coke with the New Coke. So when they came up with these results showing that the New Coke was preferred by the public, they actually took the old Coke off the shelves and they started selling just the New Coke. And the public was absolutely furious because, Coca-Cola is an iconic brand. It's almost like part of America. It's so famous around the world. It is their slogan used to be, it's the real thing. And, and people took that seriously. And so The backlash was so severe that they had to suddenly announce, oh, wait a minute. No, we didn't mean to completely get rid of Coca-Cola. No, this was just a pause. We're bringing it back out, and we're going to call it Coke Classic. Okay, so the new Coke is going to be available, but so will the so-called Coke Classic. Now, when everyone stopped being so upset, the new Coke was quietly retired, and the Coke Classic labels suddenly became Coca-Cola again. They were basically trying to pretend that none of this ever happened. It was an absolute disaster. Their sales plunged and people were fired all over the place. And in MBA schools to this day, this is a case study in marketing classes as to how not to develop new products. So sometimes, even with the best sampling methods, the wrong conclusions can be drawn from those results and disastrous decisions can be made. And this is a classic example of that. The statisticians would have said, sure, go ahead. The new Coke is preferred to the old Coke, but it didn't work out that way at all. So it just goes to show, just because you have good statistics doesn't necessarily mean you're going to make good decisions. Anyway, so yeah, that was quite a long time ago. Now you might probably on eBay, you can find for sale cans of the new Coke. I wouldn't be surprised. Oh, no, maybe not. Yeah, new Coke and strange, I don't know what that means. Stranger Things. But the new Coke, yeah, there it is. It was a catastrophe to say the least. Oh boy, I hope they learned their lessons. All right, so now what we're going to do here is when we analyze sample data, what we really want to do typically is create a handful of measures that will help us understand the properties of these samples that we're looking at. Okay, so in other words, let me just add this in here. In order to analyze a set of data, and this applies whether it's a sample or a population, it is normal. We usually create a series of measures that reflect key properties of the data. Actually, what I should do is call this numerical measures. Okay, so these measures are what we're going to focus on next. These are individual numbers that give us a lot of information about the data that we're looking at. Okay, so whether it's a sample or a population, we usually try to estimate these measures that will give us a quick look at the important details that we need to know about that data. Because usually we don't need to know the exact numbers in the data set. We need these measures. And when I introduce them to you, I'm sure you'll realize that you've seen some of these before. Now, there are different kinds of measures. Let me just mention that as well. That may be used depending on what kind of information is needed. Okay, in other words, some of these measures are more useful than others. It depends on what we're trying to find out. Okay, so we're going to see three basic types of measures. And we'll get to them all one at a time. We have measures of central tendency. And you'll see what this means when we get there, don't worry. Sounds very scary right now. So all three of these are the most common types of measures that we'll see because they all provide us with different useful information. We'll start with the measures of central tendency, and then we'll work our way up to the measures of dispersion and measures of association. All right, so the first one, measures of central tendency, are the ones where I'm pretty confident you've heard of these words before, but you might not remember what they mean. Okay, then the last two, it's possible that you've not run into these before. So along the way, what we're going to do is not only introduce these measures, we're going to introduce some new formulas, and we're also going to introduce some what we call notation or symbols that are used to represent the mathematical operations that we were going to apply in these cases. So we'll start with the measures of central tendency. And the name tells us that we're looking for basically the center of the data, the value around which the sample or population elements are concentrated. All right, so again, it's a little tricky to visualize what this means. So we'll see. We're actually going to introduce three different measures of central tendency. And it turns out each one of these has its own advantages and disadvantages. All right, here we go. So after all that buildup, we finally get to see these measures, and you're going to say, oh, I've seen these words before. Here we go. Mean, median, and mode. And I made a note in parentheses here. The word mean is simply another word for average. Now, I bet you right now you realize that you have seen all three of these before. Certainly mean or average. Everybody knows what that means. Median, you may have heard that word before without really understanding what it meant. And the same thing with the word mode, but you've probably seen them before. All right. Now, I just want to point out here, I'll add a new slide here for this, that we will often need a separate formula for computing measures for a sample and for a population. I just want to mention that right up front. Not always, but some of these, the formula, there will be a separate formula for a sample and for a population. In addition, the notation is different when describing samples and populations. In particular, Greek letters are often used to represent populations or population measures, while Roman letters, our alphabet, are used to represent sample measures. Okay, which in other words, our alphabet is a slightly modified version of the Roman alphabet. It's not exactly, it's very similar. So for the most part, the letters that we use on a daily basis were taken from the Roman alphabet. You can easily imagine why, because it was the Romans who conquered England, not the Greeks. Okay, and so that was that. Okay. And of course, you're probably aware that a lot of English words have Latin roots, although many of them have Greek roots as well, because they came along with the Roman. A lot of the Roman words had Greek roots as well. So English is kind of a grab bag of different languages. And that's one of the reasons why it's as strange as it is, why it has so many unusual rules and features that are very different from other Western European languages. Yeah, it's like you could spend a whole semester talking about just the evolution of the English language. And who knows, maybe they offer that in the English department. You might want to investigate it. It's a very interesting story. In fact, there was actually, now that I think about it, there's a very, very interesting TV series on many years ago, and it was actually called The Story of English. Man, I haven't thought about that in years. It was quite a while ago, but they really did a nice job with it. All right, but anyway, that's a topic for another day. So just be aware that when you see Greek letters, we're trying to describe a population measure. This is just a convention that's developed over the years. The Greek letters are reserved for the population measures, and the Roman letters, in other words, our alphabet, are typically used to represent sample measures. So we're going to start with we're looking at the mean, but we're going to start specifically with the sample mean. And this will give us an opportunity to introduce some very important notation. So look at this formula. It looks scary, doesn't it? It isn't, though. Once you get used to the way it's written, this X with a little line over it, as you can see up here, is called X bar. And anytime in statistics, when you see a bar over a letter like that, it is meant to indicate that this is an average of some kind. It's just the notation that was dreamed up over the centuries, and this is the one that's stuck. Now, what else is going on in here? Well, let's see. We have N down there at the bottom is the size of the sample that we're using to calculate the sample mean. So we call N the sample size. Now, then we have this symbol, which you may or may not have seen before. Oops, hold on. This mysterious looking symbol here is actually the Greek letter sigma. It is referred to in mathematics, let me make a note of that down here somewhere, as the, and we'll discuss this further in a minute, but I just want you to know this is the Greek letter sigma. And it is called the summation operator. And it basically means when you see the symbol, it means you're going to add something up. Okay. Now, the way this formula is written, though, there's other details that we need to focus on. First of all, this X with a little I next to it represents a single element in my sample. And in order to keep track of them, each one has a subscript or index, which is represented by the letter I. So if you had, for example, 10 elements in your sample, the value of I would range from 1 to 10. X1 would be the first element, X2 would be the second element, et cetera, all the way up to X10, which would be the 10th element. So the long and the short of it is that this formula simply says, if you want to know the mean of your sample, in the numerator, you add up all of the sample elements. And then in the denominator, you divide by the size of that sample. And everybody, I believe, intuitively knows that this is how an average is calculated. You just add up all the elements and divide by the number of elements. So let's say if I wanted to know the average, suppose I did a survey in this class of how long on average it takes you to get to school every day. With 25 people in the class, I would add up 25 commuting times and I would divide by 25 and I'd have my average. It's that simple. All right. So it's the kind of thing you've seen before, but probably you've never seen this very formal looking expression of it. And the reason why it's written this way is because we want it to be as general as possible. We want it to be able to cover any case that comes along. And we also want it to be easy to expand this to be used for the more complicated formulas that will be coming up later on. So that's why it needs to be written like this. But intuitively, it just means add up all your elements, and there is assumed to be n of them. Each element gets an index from 1 to 10, add them up, divide by n, and there's your sample mean. So the scary looking formula is actually not scary at all. Okay. And this sigma, you'll see it all the time in statistics. It shows up everywhere. All right. So here's a quick example on the next slide, a very simple example. Now imagine yourself in Minneapolis and you find yourself in the Mall of America, which at this point is the largest mall in the country. It's big, it's enormous, it's so gigantic. I mean, it's almost like a little city. And there's actually a mall in Pennsylvania in a city. There's a small town in the outskirts of Philadelphia called King of Prussia, which you may have heard of. And briefly, very recently, within the last few years, they expanded the size of the mall in King of Prussia. And for a short period of time, it was actually bigger than the Mall of America. But then Mall of America expanded, and now they're back to number one again. So I've never been to the Mall of America in Minneapolis, but I've been to the one in King of Prussia. And I can tell you, the first time you go in that mall, I guarantee you're going to get lost. There's so many different paths leading in every which direction. It's like I said, it feels like a small city. You can find probably 3 Starbucks just on one wing of the mall because they're so far apart from each other. So imagine yourself wondering, what is the average price of Starbucks in this mall? So you go to each of the 3. Now, if you notice, X1 represents the first Starbucks. X2 is the second Starbucks, and X3 is the third Starbucks. And in each one, the price is slightly different. Now, in practice, most likely they're all going to be the same because, they're on the same mall. But let's just say in this mall, they're not all the same for some reason. It's like gas stations. They all have similar prices, but they're not necessarily identical. And so you got all 3 of these. And so in order to calculate the average, how would that work? Good question. Well, let's see. It'll be X1 plus X2 plus X3 over 3, 2 plus 210 plus 195 over 3. So the sum in the numerator is $6.05. So at these 3 Starbucks, the average or mean price is $2. Let's round it to $2.02. And the big important detail here is that these Starbucks are a sample. They do not reflect or do not represent every single Starbucks in the country. That would be the population of interest. The population consists of all Starbucks. All of them would be the population. This is a sample. Okay. So we have a sample. Now, we may decide to use that as an average for the entire, franchise, but that may or may not be accurate. I mean, there's only 3 elements here. Normally with sampling, you try to be careful and choose a representative sample. If you're really interested in seeing how their prices are throughout the entire country, your sample would have to include Starbucks from different parts of the country. You have some in the Northeast and some in the South and some in the Midwest and some on the West Coast. This doesn't work, as this is not a really representative sample in the sense that all 3 of these are in Minneapolis. And who knows, maybe prices in Minneapolis are slightly higher than in the rest of the country, or they might be slightly lower. So this would not be a terribly good sample to analyze the entire company. But on the other hand, it might not be a bad sample for the entire mall. Let's say there's 10 Starbucks in that mall. These 3 would represent an excellent representation of all the Starbucks in that mall. Okay, so Every situation is different. These would be a good sample for the mall, but not for the entire country. All right. So yes, now the summation operator, we're going to look a little more closely at the summation operator because it's actually more general than it appears. You can do more things with it than you might realize. So we're going to take a look at some of them, and we're going to see some of these in the formulas that will show up in later parts of this chapter. Okay, so imagine the following situation. Here is a sample. So let's say that 1 week you find yourself in a hotel in Toronto, and every morning you write down the temperature in Celsius. That's your sample. I want to know what's going on with this weather in Toronto. And so those are my 5 temperatures in Celsius. And I'd like to know the average or the mean. What would I do? All right, well, of course, I'm going to add up these 5 elements. And so the summation part here, just this piece, would be x1 plus x2 plus x3 plus x4 plus x5. And that would be 2 minus 1 plus 3 plus 5 plus 1. Let's see. That's 10. Okay, so that's 10. And the mean is easy because all you have to do is divide that by 5 because there are 5 elements in the sample. And you've got an average or mean of 2. So in this sample, the mean temperature is 2. And if you wanted to, maybe that could be used to represent the temperature for the entire province of Ontario, or who knows. But the average in your sample is 2. Right, so that's not hard, is it? No, it is not. Not at all. In spite of the way it looks, it's not a hard formula. Now, let's look at some extensions of this, which you'll need later on, by the way. I don't want to, this is not just for the fun of it, although it is fun. Here's a weird setup. Look what it does. Instead of the sum of the x's, it's the sum of the x squares. I circled that too to show you that that is not the sum of the x's themselves, but the squared x's. So what that means is before you add them up, and by the way, we're using the same sample here, you have to square them individually before you add them. Okay, so in other words, when you add these up, you're adding up the squared x's, not the x's themselves. And instead of getting 10, you get 40. By the way, oh, on the top here, I just want to mention that in textbooks, what often can happen is you see the summation sign written with the index, and sometimes it's without. You don't really have to write this index unless there's something about it that's not obvious. If it's clear that you're simply adding up those elements, and a lot of times in the textbooks, they will leave those out. But sometimes the index is not exactly what we were expecting. Like, for example, the I doesn't have to start with 1. It often does, but it doesn't have to. So if you're going to do something out of the ordinary, you have to show it here. But if the information is missing, well, then you can assume that it means I equals 1 to n. Just in case you see it written down that way somewhere without the index. But anyway, the bottom line here is that by changing this to x squared, that means we have a sum of squared x's of 40 rather than a sum of x's of 10. So you can see this thing can be used for a lot of different purposes. It's not just for just adding up the numbers. And it's useful because it's a very compact notation, which explains a very complex operation in a very quick and easy way. Now, here's a bit of a twist on that. If you look at it carefully, you'll see it looks similar at first glance, but it's different. All right, so look at this one now. Now, just remember this one means you're adding up the squared x's. This one is different because the square is outside these parentheses. So what they're telling you now is you do the summation first. And only at the end do you square the results. So here, remember we added these up and we got 10. When you square 10, you get 100. So this one means you add them up and then you square them. The one on the top from the previous slide means you square them and then you add them up. So I'm going to make a note here, square, then add. Oops, that'll help us remember this. Square, then add. Here's the opposite, add, then square. Okay, and you can see they clearly gave us different results. Now the next one actually combines different steps. And again, I wouldn't introduce this to you except that we're going to need it later on in the chapter. So in the next slide, we've got a really complicated case where we have to do two things before we add them up. Here it is, okay? So with k being a constant, look at this. I've got a square in there, but I've also got a subtraction. So that means, wow, this is tricky. For each x, I not only have to subtract this k, then I have to square each one of these differences, and then I have to add them up. So there's three things going on here. Oh no. But when you see it done with an example with actual numbers, I think you'll agree, it's not quite as complicated as it looks. And once we've done it a few times, you'll never have any trouble with it. All right, it's just like anything else, you know, you just have to do it a few times and then you'll be all set. All right. It's like the first time you learn how to do anything. You have to practice. That's just the way it is. All right, now let's go back. Remember the data set that we had earlier, the Canadian temperatures? Let's bring that back and apply this formula to it. So here's the original data. I reproduced it up here again. And let's just say that our constant K is 3. So basically what we're trying to do is find out, or what we're trying to do is apply this formula so that first step, subtract 3 from each element. Once that's done, you square each difference. And then add up the results. So you can see this one is pretty messy. We have to do three things. Subtract the 3, whatever that difference is, you square it, and then you add them up. In this case, to come up with the sum of 25. All right, now that's as scary as we're going to take. I mean, you can do a lot more scary things with this summation operator. That's as scary as we need to get for this class. And you can see that these weren't really that difficult, but oh my God, you could not believe some of the things we could do with this, but not here. Okay. You can do all kinds of crazy stuff, including double sums and triple sums, however many you need. The sky's almost the limit with this stuff. All right, well, here's an example that's near and dear to your hearts. What if you've had 4 exams during the semester, and the key here is, though, that they're all equally weighted, which often is not the case. What is your average score in this class? Well, let's assign an index to each of these scores. X1 will be the 80, X2 is the 90, X3 is 92, and X4 is 99. We're going to apply this formula. So in the numerator, we're going to add up the 4 exam scores, and then when we're done, we're going to simply divide by 4. All right, so I'll show you the details in the next slide. So once again, these are the 4 test scores. This is the formula. So the sum in the numerator is just x1 plus 2 plus 3 plus 4, which adds up, as you can see, to 361. And then all that remains to be done is to divide by the sample size of 4, and you end up with 90.25. That's your semester average. Hopefully they'll give you an A for that. Well, technically it's an A minus, but you never know, you might get a curve. So, but this average is 90.25. Now, just because, you know, at this point in the course, we're getting to be pretty good at math now. I mean, after all this time, I think we're starting to remember how interesting math really is. And whenever there's an opportunity to learn more about it, we're going to gladly take it, aren't we? Yes, I just want to just point out here, just as a side note, note this type of average that we've just calculated. Hold on one second. I'm trying to make it a little prettier. This type of average is known as an arithmetic average. There are other types of averages that are used in different circumstances. These include the geometric average, which is often used with stock prices, by the way, and the harmonic average, which is, I'm not even sure when we would use that, but I just want to throw that out there. So in case you run into these words in another context, arithmetic average is what we're doing here. Okay, but there are other ways of calculating averages, which we will not do in this class. And again, these are meant for more specialized conditions for certain, like for example, like I said, if you have a portfolio of stocks and you want to calculate the rate of return to those stocks, then in that case, it makes more sense to use the geometric average. But for our purposes, we will only use the arithmetic average. In other words, add them up and divide by the sample size. Now, what about the population version of this formula? All right, well, I'm going to show it to you. And you can see there's some important differences, which I've already circled and put arrows there. This letter here is actually the Greek letter mu. And this is going to be used to represent the population mean. And remember, I did mention once before, Greek letters like mu are used to represent population measures, and this is no exception. Okay, and so I just want to remind you, this is a Greek letter, mu. It's the equivalent, it's the Greek version of M. And so if you look here, we're doing exactly what we did here. This is our sample mean. Just a quick reminder, if you look at the two, they're essentially identical except for the mu. And also the convention we'll use here for the population is that the capital N is used for population size. Whereas remember before, lowercase n was the sample size. Why do we need to do this? Because there are formulas that require both numbers, and we have to have a way of telling them apart. And the way we'll do that is to have lowercase n for the sample size and capital N for the population size. All right, does that make sense? Yes. So now the actual process is exactly the same. We will take our population elements, add them up, and divide by the size of the population. So it's exactly the same, except that we're writing it with slightly different notation. Okay. So yes, and as I mentioned before, we use the Greek letters for population measures and Roman letters for sample measures. All right, so let me just throw in a quick example there, just to completely reinforce this. Okay, a population consists of the farms in a certain county in Idaho. Now, of course, you know the population is pretty sparse in Idaho. And the population, actually what I should say is the size in hundreds of acres of the farms in a certain county in Idaho. All right, so in other words, each element of the sample is the size of a farm. These are, and then we have 20, 25, 34, 52, and 100. And let's say, I don't know, 110. Okay, so those are the 6 farms in this county. And those are their sizes. So I'll copy these under the next slide. What is the average in this county? Okay. So what you're going to do, and now this time it's a population, but the calculations will not be affected. So the formula, of course, is mu is the sum over the population size. So we'll have 20 plus 25 plus 34. It's 52 plus 100 over 6. Because there's 6 farms in this county. Remember, it's a very small county. I mean, the population is very small. So when you add these up, let's see what they add up to. $341 over 6, which works out to be 56.83. So the average farm in this county has roughly 5,600 acres, 57, I guess we could round it to. So that's an example of how we would calculate the mean of a population. And you notice it's exactly the same, except for the notation. Okay, so that's that. Now, let's go back and revisit this example with the GPAs. In this case, when the grades are equally weighted, we can calculate an average by simply adding up the 4 scores and dividing by 4. Now, most of the time, as you know, the grades during a semester do not carry equal weight. Often the final exam is weighted more than the earlier exams. How do we calculate an average when that's the case? Well, for that situation, we need a special type of mean, which is related to what we're doing. And it has a very special name. It's called a weighted average. So weighted averages are useful when we have a data set that has many repeated values, or else some elements are worth more than others in the sense like the grades or the GPAs. So here we're not going to simply add up the numbers and divide by the sample size. We have to do something a little bit different. So we're going to start out with a simple case. Now, first of all, I'm going to show you the formula, and don't be horrified when you see it. We're going to assume, let me just add this in here. Each sample or population element has associated with it a weight which reflects its relative importance. In the data set. Okay, so every element is assigned to it what we will call a weight, which reflects its relative importance. Now, just as let me just mention this. Maybe this will be a good example. If you've never heard of this, the Standard & Poor's 500 is a stock market index which reflects the prices of the 500 largest corporations in the US. So since Apple stock, or Apple, is the largest US corporation, and that's measured as market capitalization, or the value of its stocks. That means that its price has a larger influence on this index than the prices of smaller companies. Okay, so I don't know if you've ever heard of the Standard & Poor's 500 or not. It's often abbreviated the S&P 500, but it's set up so that the prices of these stocks are used, but in such a way that their value depends on the size of the company. So in other words, when Apple's stock changes, it's going to have a huge impact on the Standard & Poor's 500. But when a tiny little company does not, I mean, theirs will not have anywhere near the impact. It's a weighted average. Let me just add this one little detail. I think I left this out. It is calculated as a weighted average. Okay, that's the important detail. I left that out by mistake. It is calculated as a weighted average. It's not, they don't just add up the 500 prices and then divide by 500. It's a weighted average. Now, here's the formula. Now, again, let me show you, this is the sample. This is how you would calculate the weighted average for sample. And again, don't be horrified by this formula, because it looks messy, but it really isn't. Because you've got just this one new element, Wi, which is the weight of element X. Okay, so remember we said each element gets its own weight. And so here, all of a sudden in the numerator, you have the sum. And notice what I've done here. I'm actually multiplying two terms together. Each X is multiplied by its own weight before we add them up. In other words, this can be thought of as W1x1 plus W2x2 plus all the way out to Wnxn. In the denominator, it's very simple. We're just adding up the weights. Okay, now I just want to mention that depending how the weights are defined, sometimes the weights are guaranteed to add up to 1 and sometimes they're not. It depends on how they were defined in the first place, but all that's telling us is to add up the products of the weights and the x's in the numerator, and in the denominator, we're adding up the sum of the weights. And when we're done, we have our weighted average, which you notice is still represented as X bar because this is the sample mean. Okay. And there'll be the equivalent, and I'll just show it to you on the next slide. There's an equivalent version for the population where all we change, as you can guess, is that the X bar is replaced by mu and the lowercase n's are replaced by capital N. All right, so let me just quickly show it to you. And they're both, I put them side by side so you can review quickly the differences between the two, but you can see it's the same thing. It's just different because of the mu and the N, capital N, and that's it. That's your sample mean, or I'm sorry, weighted mean for the sample and the population. All right, now there's an example coming up, but it's a fairly complicated, time-consuming example. And so I'll tell you what, why don't we save that for next week? Now, next Monday, of course, we'll have class as usual, but next Thursday, we're not obviously meeting because that's Thanksgiving. And so we'll continue with chapter 12 for a while. We're not quite ready for those videos that I was talking about earlier, so we'll save those for next time as well, or we'll save that for the future as well. And by the way, I'm noticing for some reason the Zoom has continued to work the whole period this time. I'm kind of surprised. I don't know what changed, but it has been working. It didn't blow up on us, so I guess that's progress. So anyway, so we'll meet again next Monday as usual, and we'll carry on from here. And then we'll have Thanksgiving break. And when we get back, we'll wrap up chapter 12. We'll do the chapter 12 problem set. And at some point we'll do the sample final, and then that, sadly enough, will be the end of this class. So don't worry, there's plenty more math classes available if you want them. So you don't have to feel like this is the end of your math career if you don't want that. Okay, if you do, well, your math skills are quite strong now, and so you'll be able to use them hopefully in your future endeavors. So all right, so I guess we'll just knock it off here, and I'll see you all next Monday. All right. Uh-oh, I may have spoken too soon. This thing it's not working, is it? Oh no. Ugh. Oh no, here it is. Okay. No, maybe not.